Hi, and welcome to Physics 2211 Lab 4. This will be the table of contents for my lab report. The purpose of this lab was to analyze the motion of a spring mass system based on a computational model and observe results. In this lab, we also analyzed energy changes that occurred within the system to verify the energy principle. Starting off with some key principles, Newton's second law states that the net force equals to a change in momentum over a change in time. Newton's second law can then be used to derive the velocity update formula, where the final velocity vector is given by the initial velocity vector plus the acceleration multiplied by a discrete time step delta t. We also have the position update formula, which will be used extensively in our computational model. The position update formula shows that the final position vector is given by the initial position vector plus the average velocity vector multiplied by time step delta t. The energy principle is given as follows, where the change in energy of a system, delta E, is given by the sum of the work done on the system by the surroundings and the heat transfer between the system and the surroundings. This vector equation for the spring force is given as follows, where K represents the spring's stiffness, L represents the length of the spring, and L naught is the rest length of the spring. Finally, there are different types of energies. Kinetic energy is given by half mv squared, where m is mass and v is speed. Spring potential energy is given by half ks squared, where k is the spring constant and s is the amount of stretch or compression. Gravitational potential energy is given by mgh, where m is mass, g is acceleration due to gravity, and h is height. The period of a spring is given by the following formula, where t is the period, m is the mass, and k is the spring constant. The formula will be used to determine stiffness of our spring based on the measured period. It was then found that the predicted and observed trajectories were similar in both the x and y axes, with both following a sinusoidal curve. The computational model ended up predicting a total energy change of 0 joules. The changes in the kinetic energy and potential energies oscillated in a sinusoidal manner, which also reflects this fact. For the tracker analysis, the spring reached an equilibrium length of 0.7 meters. This was used to calculate the rest length of the spring, which turned out to be 0.123 meters. The mass was 0.402 kilograms, and the spring constant was 6.83 newtons per meter. Here, our system consists of the mass, spring, and earth. The surroundings consist of nothing else, as we expect no external work to be done on the system. The position of the mass was then tracked frame by frame, as shown in this video. The x and y coordinates were then recorded and stored in a CSV file. For the computational model, the initial conditions are shown here, where the Bohr's mass was set to 0.402 kilograms. The Bohr's position was taken from the CSV data and implemented in the program. The Bohr's initial velocity was calculated by taking the displacement between the first two measurements and dividing by the time interval between them. The series of calculations is shown in the table on the bottom of the screen. In this part of the code, we set gravity to be 9.8 meters per second. The spring constant was then set to 6.83, and L naught was set to 0.123 meters. Next, we defined the L vector and S, the magnitude of displacement. From there, we used our formulas for the kinetic and potential energies and implemented them here. In the final line, the total energy is given as the sum of the kinetic and potential energies. In the simulation loop, we first defined the initial energies. Next, we defined force due to gravity and the spring force. The net force is given by adding the force from gravity and spring together. Next, we used the velocity and position update formulae by applying the momentum principle. Finally, we recalculated the kinetic and potential energies. We also calculated the change in energy by subtracting the final energy from the initial energy. When the simulation was run, we achieved this graph of the change in energy versus time. Here, the change in total energy is represented by a flat line at 0, demonstrating that the net change of the entire system is 0. The other changes in energy, on the other hand, trace out sinusoidal patterns with their amplitudes ultimately adding to 0. On the left is a graph of the x position versus time, and on the right, the graph represents the y position versus time. On the left, we see that the computational model very accurately predicts the x position of the mass over time, with very similar period of oscillation and amplitude. The graph on the right shows the model having the same period of oscillation. However, it predicts a slightly larger amplitude of oscillation. One source of error between the observations and computational model may have been due to the inaccurate position tracking with the tracker software. As the mass moves, it may have been difficult to pinpoint the exact center of mass, which would result in some slight error. The tracker video may have also had some amount of parallax error, which would result in a distorted view of the mass's movement. The tracking was also made more difficult due to poor video quality. Additionally, the computational model did not account for air resistance, which may have led to some very slight deviations from the observed motion. From this lab, we can ask if the energy principle is satisfied. We can say that yes, it is satisfied. The energy change graph displayed here shows that the total energy change is 0. This is to be expected due to the fact that there is no external work done in the system, nor is there any heat transfer. We can also see from the graph that any change in one form of energy is met by a corresponding increase or decrease in other forms of energy, with a net change of 0 joules. We can also ask what the periods of oscillation are for the x and y positions. For the x position, the time taken for 5 wavelengths to pass was used to minimize the uncertainty in the calculation. As shown in this graph, the time it took for 5 wavelengths to pass was 8.264 seconds. 8.264 divided by 5 gives a period of 1.65 seconds. For the y position, the time taken for 5 wavelengths to pass was 7.645 seconds. 7.645 divided by 5 gives us a period of 1.529 seconds. When compared to the period for a simple pendulum, we can assume the spring has an average length of 0.7 meters. From this, we see that the theoretical period is 1.68 seconds, which closely matches the measured value. For the mass spring system, we can also use another formula to calculate a period of 1.524 seconds. The fact that these values match very closely suggests that there is minimal coupling between the horizontal swinging and vertical bouncing. Here, the horizontal motion behaves like a simple pendulum, whilst the vertical motion behaves as a simple mass spring oscillator.